National Electrical Code Section 240.21 subsection B governs tap conductors. This section states that tap conductors over 10 feet long shall not exceed their source circuit ampacity. National Electrical Code Section 240.4 subsection addresses the protection of conductors and equipment. It states that conductors and equipment must be protected from overcurrent by an appropriate overcurrent protective device. National Electrical Code Section 380.3 subsection B pertains to overcurrent protection. This section dictates that a feeder shall be protected at its origin and at each point of supply. Now let's apply these code sections to a design scenario. Imagine a system with two sets of 250 kc mil copper conductors fed from a 600 amp adjustable trip breaker to a 50 flow gutter. From this gutter, there is a 100 amp tap with a fuse switch for a rooftop unit, or RTU, and a 400 amp tap to an existing 400 amp main lug only, or MLO, panel loaded with single pole 20 amp breakers. The question is whether the 400 amp panel requires a 400 amp main circuit breaker or MCB. Considering the tap rules, the 250 kc mil conductors from the breaker to the gutter are not in question as they are assumed to be less than 10 feet long. The 100 amp tap to the rooftop unit, which is protected by a fuse and is within the 10-foot tap rule, does not require an additional overcurrent device. However, the 400 amp tap to the existing 400 amp main lug only panel presents a code compliance issue. If this tap exceeds 10 feet and lacks overcurrent protection at its origin, it violates the tap rules and overcurrent protection requirements. The code mandates the installation of a 400 amp main circuit breaker at the origin of the feeder to protect the conductors and equipment within the 400 amp panel. The length of the bus within the 400 amp panel is not considered part of the tap conductor length for the purposes of the 10-foot tap rule. Therefore, it does not exempt the panel from requiring an overcurrent device at the tap's origin. To summarize, a 400 amp main lug only panel requires a 400 amp main circuit breaker to protect the conductors and equipment within the panel. It is recommended to revise the design to incorporate a 400 amp main circuit breaker at the origin of the feeder to the 400 amp main lug only panel, ensuring compliance with the National Electrical Code and safeguarding the electrical system against overcurrent. In more detail, let's consider the ampacity of the 250 kc mil copper conductors. According to NEC Table 310.15b16, 250 kc mil copper conductors with a 75 degrees Celsius insulation rating have an ampacity of 255 amps in the raceway or cable. Since there are two sets of these conductors in parallel, the total ampacity is 2 times 255, which equals 510 amps. The 600 amp adjustable trip breaker must be set to a value that does not exceed the conductor ampacity. Therefore, the breaker should be set at or below 510 amps. Now, let's consider the 100 amp tap to the rooftop unit. If the tap conductors are sized to carry at least 100 amps and are protected by a 100 amp fuse at the point where they connect to the rooftop unit, the tap meets the requirements of NEC Section 240.21b2, which allows for taps not over 10 feet long without overcurrent protection at the tap's origin, provided the tap conductor's ampacity is not less than the rating of the device or overcurrent protective device supplied by the tap conductors. Moving on to the 400 amp tap to the main lug only panel, the length of this tap is critical. If the tap conductors are longer than 10 feet, NEC Section 240.21b3 applies, which states that the tap conductor's ampacity must not be less than 1/3 of the overcurrent device protecting the feeder conductors. In this case, the feeder conductors are protected by a 600 amp breaker. 1/3 of 600 amps is 200 amps. Therefore, the tap conductors must have an ampacity of at least 200 amps. Furthermore, the tap conductors must terminate in a single circuit breaker or a single set of fuses rated not more than the tap conductor's ampacity. Since the tap is feeding a 400 amp main lug only panel, the tap conductors must be sized to carry at least 400 amps. This typically requires larger conductors than what is minimally required by the 1/3 rule. The main lug-only panel itself does not provide overcurrent protection for the tap conductors. This is because the main lug-only panel is designed to distribute power to multiple branch circuits, each with its own overcurrent protection. The main lugs simply provide a connection point for the incoming feeder conductors. Therefore, a 400 amp main circuit breaker is required at the origin of the tap to protect the tap conductors and the equipment in the main lug-only panel. This breaker must be rated at 400 amps or less, depending on the ampacity of the tap conductors. Now, let's consider the existing 400 amp main lug-only panel. It is loaded with single-pole 20 amp breakers. The total connected load of these breakers must not exceed the capacity of the panel or the tap conductors. If the total connected load exceeds 400 amps, the panel may be overloaded, which could lead to overheating and potentially a fire. To determine the actual load on a panel, a load calculation should be performed in accordance with NEC Article 220. This calculation takes into account the demand factors for various types of loads, such as lighting, receptacles, and appliances. The demand factors are based on the assumption that not all loads will be operating at the same time. Once the load calculation is complete, the total calculated load can be compared to the capacity of the panel and the tap conductors. If the calculated load exceeds the capacity, steps must be taken to reduce the load, such as by adding additional panels or by replacing some of the loads with more energy-efficient equipment. In addition to the load calculation, it is also important to ensure that the branch circuits in the panel are properly sized and protected. Each branch circuit must be protected by an overcurrent device, such as a circuit breaker or fuse, that is rated to protect the conductors and equipment served by the circuit. The size of the overcurrent device must be in accordance with NEC Table 240.4b, which provides the maximum allowable overcurrent protection for various sizes of conductors. For example, a 14 American wire gauge copper conductor with a 75°C insulation rating has an ampacity of 15 amps and is typically protected by a 15 amp circuit breaker. A 12 American wire gauge copper conductor with a 75°C insulation rating has an ampacity of 20 amps and is typically protected by a 20 amp circuit breaker. A 10 American wire gauge copper conductor with a 75°C insulation rating has an ampacity of 30 amps and is typically protected by a 30 amp circuit breaker. It is important to note that these are just general guidelines, and the actual size of the overcurrent device may need to be adjusted based on the specific application. For example, if the branch circuit serves a motor, the overcurrent device may need to be sized larger than the conductor ampacity to allow for the motor's inrush current. Finally, it is important to ensure that the electrical system is properly grounded and bonded. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electric shock. Bonding connects all of the metal parts of the electrical system together, which helps to prevent voltage differences from developing between them. The grounding and bonding requirements are covered in NEC Article 250. In summary, the design in question requires a 400 amp main circuit breaker at the origin of the 400 amp tap to the main lug-only panel. The length of the bus within the panel is not considered part of the tap conductor length for the purposes of the 10-foot tap rule. A load calculation should be performed to ensure that the panel is not overloaded. The branch circuits in the panel must be properly sized and protected. The electrical system must be properly grounded and bonded. By following these guidelines, the electrical system will be safe and reliable. Now let's delve deeper into the NEC requirements for tap conductors, focusing on scenarios where the tap conductors exceed 10 feet. As previously mentioned, NEC Section 240.21b3 governs these situations. This section outlines several conditions that must be met to ensure the safety and proper operation of the electrical system. Firstly, the tap conductor's ampacity must not be less than 1/3 of the rating of the overcurrent device protecting the feeder conductors. This requirement ensures that the tap conductors are adequately sized to carry the available fault current without overheating or causing a fire. Secondly, the tap conductors must terminate in a single circuit breaker or a single set of fuses rated not more than the tap conductor's ampacity. This requirement prevents the tap conductors from being overloaded by a downstream load. Thirdly, the tap conductors must be installed in a raceway or be otherwise protected from physical damage. This requirement helps to prevent damage to the tap conductors, which could lead to a short circuit or other electrical hazards. Fourthly, the tap conductors must not penetrate a wall, floor, or ceiling. This requirement helps to prevent the spread of fire from one area to another. Fifthly, the tap conductors must be readily accessible. This requirement allows for easy inspection and maintenance of the tap conductors. In addition to these specific requirements, there are also several general requirements that apply to all tap conductors. These requirements include the following. Firstly, the tap conductors must be properly identified. This requirement helps to ensure that the tap conductors are not accidentally disconnected or damaged. Secondly, the tap conductors must be installed in a neat and workmanlike manner. This requirement helps to ensure that the tap conductors are properly supported and protected. Thirdly, the tap conductors must be inspected and tested before being put into service. This requirement helps to ensure that the tap conductors are properly installed and are operating correctly. Now let's consider some specific examples of how these requirements apply in practice. Imagine a scenario where a 400 amp feeder is protected by a 400 amp circuit breaker. A tap is taken from this feeder to supply a 200 amp panel. The tap conductors are 25 feet long. In this case, the tap conductor's opacity must not be less than 1/3 of 400 amps, which is 133.3 amps. The tap conductors must terminate in a single circuit breaker or a single set of fuses rated not more than the tap conductor's opacity. The tap conductors must be installed in a raceway or be otherwise protected from physical damage. The tap conductors must not penetrate a wall, floor, or ceiling. The tap conductors must be readily accessible. Another scenario involves a 600 amp feeder protected by a 600 amp circuit breaker. A tap is taken from this feeder to supply a 100 amp panel. The tap conductors are 15 feet long. In this case, the tap conductor's opacity must not be less than 1/3 of 600 amps, which is 200 amps. The tap conductors must terminate in a single circuit breaker or a single set of fuses rated not more than the tap conductor's opacity. The tap conductors must be installed in a raceway or be otherwise protected from physical damage. The tap conductors must not penetrate a wall, floor, or ceiling. The tap conductors must be readily accessible. It is important to note that these are just examples, and the specific requirements may vary depending on the specific application. It is always best to consult with a qualified electrical engineer or contractor to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. By following these guidelines, the electrical system will be safe, reliable, and code compliant. The purpose of overcurrent protection is to protect conductors and equipment from excessive currents, which can cause overheating, insulation damage, and potentially fires. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. Circuit breakers are electromechanical devices that automatically open a circuit when an overcurrent condition is detected. They can be reset manually after the fault has been cleared. Fuses are overcurrent protection devices that contain a fusible link that melts and opens the circuit when an overcurrent condition is detected. Fuses must be replaced after they have blown. The selection of the appropriate overcurrent protection device depends on several factors, including the opacity of the conductors being protected, the interrupting rating of the device, and the type of load being served. The opacity of the conductors is the maximum amount of current that the conductors can safely carry without overheating. The overcurrent protection device must be rated to protect the conductors from overcurrent, but it must not be rated so low that it trips unnecessarily under normal operating conditions. The interrupting rating of the overcurrent protection device is the maximum amount of fault current that the device can safely interrupt without being damaged. The interrupting rating must be high enough to handle the available fault current at the point where the device is installed. The type of load being served can also affect the selection of the overcurrent protection device. For example, motors typically require overcurrent protection devices with time delay characteristics to allow for the motor's inrush current during starting. In addition to protecting conductors and equipment from overcurrent, overcurrent protection devices also provide protection against short circuits and ground faults. A short circuit is an unintended connection between two or more conductors. A ground fault is an unintended connection between a conductor and ground. Short circuits and ground faults can cause very high currents to flow, which can quickly damage conductors and equipment. Overcurrent protection devices are designed to quickly interrupt the flow of current in the event of a short circuit or ground fault, thereby minimizing the damage. The National Electrical Code provides detailed requirements for overcurrent protection. These requirements are designed to ensure that electrical systems are properly protected from overcurrent, short circuits, and ground faults. It is important to consult the NEC when designing and installing electrical systems to ensure that they are safe and code compliant.